Okay, so today we're learning about some consequences of Gauss curvature. And also the second fundamental form, the principal curvatures. So various theorems about curvature of surfaces in R3. So first of all, we have a definition. And just for the record, vocabulary is not my strong point. It's not my favorite thing. And I think that's true of a lot of mathematicians because the words they come up with are very bizarre. So imagine you have a surface. Now at each point, of course, I tend to choose the point at the top here, but it's easier for me to draw the tangent plane, but I'll go off to the side today, right? There's you've got a tangent plane there, right? This is the point P. And then the shape operator maps that tangent plane to itself. It's a linear operator and has eigenvalues and eigenvectors. And so we're defining, here's our notation that we'll be using. Or I think they use U1 actually. Don't they use U1 for the vectors? So the point is we can represent the shape operator by this matrix K1, K2, 0, 0 with respect to the basis U1, U2. And that's an orthonormal basis. Orthonormal basis, right? Because eigenvectors we can choose to have length 1. And we know when K1 is not equal to K2, you can prove that K1 and K2 have to, that U1, U2 have to be perpendicular. Right, we've done that 2 lectures ago, I think. And let's see what else. If K1 equals K2, then the shape operator is just multiplying everything, assuming U1, U2 are linearly independent, then everything is just multiplied by K, and so you can still choose an orthonormal basis. It's just that every vector is an eigenvector. And so that's what K1 and K2 are. Now, what are some special points? Definition, and this is, I have no idea where this word comes from. An umbilic point is a point P where K1 equals K2. Okay? I mean, it could happen, right? Usually K1 and K2 will be distinct. I tend to like to have K1 less than or equal to K2 because 1 is less than or equal to 2. But I'm not sure that the book always respects that convention, and nor do you have to. It's just, why not? And so then that raises the question, well, what does that mean, right? Well, we know, can anyone give me an example of a surface where K1 equals K2 everywhere?
Sphere.
A sphere. Great example, right? Can anyone give me an example of another surface?
Plane.
Yeah, plane. Can anyone give me an example of another surface?
Tip of a cone.
Shape operator is not defined on the tip of a cone because the tangent plane's not. Wait a second. Yeah, tangent plane's not really defined, right? Because what's the velocity vector of a curve that has a corner in it, right? That first derivative, it's discontinuous, right? So that's you raise a very interesting question. Like, what is the shape operator, the tip of a cone, right? Well, but right now we have not defined the shape operator in that context. The way I think of it, by the way, just even though we won't go this direction right now, is I would always take something that's not smooth, like the cone, right? And then round it out a little bit, and then take a limit, right? So I'd always think of a cone with a corner or that sharp tip, right, as the limit of these smooth things, right? And then I can talk about the smooth things, and then take limits. So can anyone give me an example of a surface where the whole thing has, every point is umbilic, that's not a sphere and not a plane? By the way, if you have a plane, the shape operator is just 0, so K1 equals K2 equals 0, right? Yes?
Does the helicoid have that property?
The
The little
helicoid,
spiral.
the DNA thing, right?
Yeah.
No, it doesn't. But, good guess. And this is the game people play when we make conjectures, because we're like, and then people go for a long time and they're like, I can't think of another one. And so then someone conjectures and says, conjecture. A surface, I'll write it out, conjecture. A surface consisting entirely of umbilic points is a plane or a sphere. That's how you make conjectures, is examples, right? And then someone asks a question. Okay, so we got a plane, we got a sphere. You don't think of anything else. And then we check the helicoid, have to do a computation, right? But if you check it, it turns out no. And then you make the conjecture. And then that conjecture might stick around for a day, an hour, a day, a week, a month, a year, a decade, a century, right? Right? There are open problems that are over 100 years old. I'm not sure what the oldest conjecture is. Actually, someone might Google that. I'm kind of curious. What's the oldest unsolved problem, right? It could be something very, very stupid, like, imagine, what could they be thinking about thousands of years ago, right? What conjecture could they have made that we haven't been able to prove one way or the other? Actually, it's kind of an interesting question.
Gold box conjecture.
Okay, which one is that? Is that the one about...
Every natural number greater than 2 is the sum of 2 prime numbers.
Okay, right. There's also the twin prime conjecture, right, which is still open. But how old is the Goldbach conjecture?
It was first articulated in 1742.
And that's the oldest conjecture?
Well,
Great question.
It's one of the oldest and best known unsolved problems.
Okay.
Which I'm sure that there's a very trivial.
Because come on, the ancient Greeks didn't ask a question. We've answered all the questions the ancient Greeks and the ancient Chinese civilizations came up with. But maybe we don't have a record of the questions. I mean, probably not, right? Maybe we just don't have a record of some of their questions. Okay. Yeah. So the sum of every even number, every even number is the sum of 2 primes. Is that the conjecture?
Yeah.
Question.
Yeah, the Goldbach conjecture?
Yeah.
Okay. Every even number bigger than 4 or whatever. I mean, because so let's see here. So 4 is 2 plus 2. 6 is, I mean, are we counting 1 as a prime number? That's the thing. Usually not, right?
One's not.
So 6 is 3 plus 3, right?
Mm-hmm.
And then 8 is 5 plus 3 and so on, right? So so I'm not counting 2, I guess. Right, so 2 is an even number.
Right.
It's not the sum of. So other than 2, right? Every positive even number is the sum of 2 primes?
Even natural number greater than 2.
Greater than 2, okay, great.
It's been shown to be true up to all integers less than 4 times 10 to the 18.
So there's now, do you all think the Goldbach conjecture will ever be proved? 1742 is that what you said?
Yeah.
Okay. I mean, I would love to prove it. How about you guys? Would you love to prove that? Every even number is the sum of 2 primes? I mean, I'll take that. Solve the oldest. I mean, it's a famous problem, right? There's also, of course, the twin prime conjecture, which is there infinite number of twin primes. What's a twin prime? It's 2 primes that differ by 2, right? So 3 and 5, 11 and 13.
Oh, there's a related one which was proved, which is that every odd number greater than 5 is the sum of 3 primes. And we proved that one.
When?
2013.
Who did that, by the way? Let's acknowledge them. That's us. Because that's
Harold
not.
Helfgott.
And where is he at?
He is Peruvian.
Okay. So, I mean, this is what mathematicians do, right? Sit around trying to prove things, and I have no idea how Harold Helfgott
Yeah.
did that, right? I'm surprised I don't know his name because that sounds like a pretty cool result, actually. Right now, it's not the conjecture, right? But it's getting closer. What did he do? Okay, let's examine what Harold did. Okay. He said, "Well, is there an easier problem I could solve?" And then he said, "Well, is there an even easier problem?" And let me guess. He showed that any odd number is the sum of 3 primes. I bet you before that he showed that any even number is the sum of 4 primes, or every odd number is the sum of 5 primes, right? He probably said, okay, come on, some of these problems must be easier, right? He came up with a bunch of them, ranked them in order of difficulty based on his understanding of the subject, right? And then started proving the easiest ones first. And I just want to point out that that's very important, okay? Also, you run computer programs to see which of these conjectures are even true, right? And so it's been checked up to gazillions, right? Some astronomical number, however high computers can go, which is super high. I proved a conjecture once. I mean, it's my job, right? Mine was conjectured by Sir Roger Penrose in 1973. Penrose won the 2020 Nobel Prize in Physics for his contributions to mathematical relativity. One of those, he proved some really cool singularity theorems about black holes and the Big Bang, but he also, one of his contributions was to make some cool conjectures. And the coolest conjecture he made about black holes is the conjecture that I proved. And the paper appeared in 2001. So by that measure, it would be like a 28-year-old conjecture. And guess what? I've been living off that accomplishment ever since, right? I can just sort of quote. No, no, it's in some sense that is sort of the life cycle of a mathematician, right? You're always going to have your best thing, right? I spent 5 years working on that problem, right? It's kind of hard just to duplicate. You know, you spend, you know, it's a lot, right? And so if it takes you 5 years to do something, you know, that makes you known, right? It's like, okay, by the way, you could spend 5 years on it and not be successful, right? So that's the thing where it's like, if you were guaranteed, oh, okay, yeah, which conjecture should I solve? Only take 5 years? Oh, okay, great. I'll solve this one, right? But you don't know, like you may never, in fact, the reality is, you know, even just to put what I did in perspective, because I understood, I was there, so at least I can comment on that, right? Is I didn't do it by myself. That's ridiculous. No one ever does anything by themselves, right? So first I had to get a really strong math education. Then I went to Stanford, where probably the #1 person in the world thinking about this problem was, right? Which was why, and then I was, you know, we negotiated on a project. He said, here, why don't you think about this problem, right? And that took his insight, like, you know, what confidence he had in me to give me this problem, right, when I was just like a second-year grad student, right? And said, here, why don't you think about this, right? And then he'd already been thinking about it for, you know, decades, let's say, right? You know, 15 years at least. You know, off and on, right, in his area, right? And then he was generous and shared with me. This is Richard Shane, my former thesis advisor, and he shared with me all of his ideas that didn't work, right? Which is huge. You guys realize how huge that is? To understand, okay, don't do this, that doesn't work. Watch out for this, that doesn't work. By the way, sometimes people tell you ideas that don't work, but they do work. But not the way they did it. Do you guys understand? So that's called, I mean, what do you call that exactly, right? That's like misinformation. And everyone has it. Like, everyone has misconceptions. Like, we're all at the edge of what we understand, right? So you got to watch out for your misconceptions. Make sure the picture in your head is as accurate as it can possibly be, right? And then what you do is you say, well, I can't solve that problem, but how about an easier problem, right? And you start doing special cases. What if I assume spherical symmetry, blah, blah, blah. Can I make some progress here? Can I make some progress there, right? And this is the fun of mathematics. If this sounds like super like fun and exciting to you, maybe you might want to be a mathematician, right? This is what mathematicians do. And to me, it was super exciting, and I made some partial progress in my thesis, and it was a nice thesis, got me a job. And then my first year out of grad school, I moved to Boston, and had a NSF postdoc funded. It was funded by NSF at Harvard, and I had no teaching. I made almost no money, and I had no friends. And nothing else, because new city, right? I had like one friend, and nothing better to do than to think really hard about this cool problem, right? And that is actually the kind of environment where you can really focus and concentrate, no distractions. And so I was able to come up with an idea. December 2nd, 1997, still remember the day. It was like, I realized I'm going to solve this problem. I had a new idea, and it worked. And it took me 2 years to write the paper. and then 2 years for them to referee it, and then 2001 the paper appeared. So, and by the way, the 2 years to write the paper, there was a lot of math going on there too, because you have a sketch of an idea, but then you got to work out all the details, right? It ended up being like an 80-page paper, right? And there's a whole bunch of details, right? But there was, a core idea I understood on that first day. So that's what mathematicians do. And so, when we run across a conjecture, this is actually not too bad a conjecture, right? It's just a relatively straightforward one. And in fact, it's a theorem, right? But I just want to present it as a conjecture first, right? And now the book, first you conjecture it, you try to find counterexamples, and then you prove it, right? And so when you see this theorem about to present to you, then you're like, oh, wait, how did anyone ever come up with this? Well, after exhaustively checking that it's true, first of all, right? Okay. So, how do we prove this? I mean, let me tell you what the hardest thing to prove is, and if you spend any time trying to prove things, you'll run across this. The hardest thing, in fact, the hardest thing to prove is something that's so hard to prove, no one's ever actually been able to do this actually successfully. Sometimes people think they've done it, but no one has actually been able to prove something which is false. Right? If you try to prove something, if you try to prove 2 equals 1 without breaking the rules of logic, right? Good luck with that. Right? And some people have spent their lives, by the way, quite literally trying to prove 2 equals 1, not realizing that's what they were doing, right? So examples and counterexamples are super important. But then once you realize, no, I've checked all the examples and counterexamples, this has definitely got to be true. There's just, and you can imagine how one might, there's all kinds of work that goes on in the background. Then the question is, well, how do we prove this, right? So the trick is to compute u, uv 2 different ways, okay? So remember what u is. U is this normal vector at each point. And so we're going to compute its covariant derivative 2 different ways. So by taking the u derivative first, and then by taking the v derivative first. So remember that if we look at the covariant derivative in the x, v direction of u, this is the same thing as u sub v, right? And we've proved it here in class before. And make sure you understand that, right? That this is also the partial derivative of u in the direction of v. Why? What does this mean? It says go in the direction of v, I mean u and v, go in the direction of v, which is, by definition, u is being held fixed in this direction. This is the direction corresponding to v increasing at speed 1 and u not increasing at all. So this is u sub v, and then if you take the covariant derivative in the x u direction, then that's a u derivative added on to it, so that's x uv. And the order here doesn't matter because partial derivatives commute. But on the other hand, you could, like we said, you can do it the other direction as well. We could also do xv, xu. Oops. And that also equals capital U, uv. Okay, so what we're going to do is we'll have the k1 equals k2, right? Everywhere, so we'll go ahead and let that equal k. The definition of k. But then you look at this, it means the shape operator, these guys are eigenvalues. And so this means that the covariant derivative in the xu direction of kx, this is covariant derivative in the xu direction of kxv. Thank you. Yes, because the shape operator is the negative covariant derivative. So let's yes, negative. Do the same operation down here. And then now we have to use the product rule here, because now here's the interesting thing: the sphere and the plane they're on bullet points everywhere, but that k is a constant function of u and v, right? It's constant, right? You have, in fact, for the sphere, it's 1 over r, and for k, for the plane, k equals 0, right? But as far as we know right now, k is a function, right? So k, we can think of as a function of u and v. There's no reason to think that it's a constant, right? Potentially could vary from point to point. So this is a little bit of a subtle point. K1 equals K2 everywhere, but what that value is doesn't have to be the same everywhere, right? It could be, at this point, K1 and K2 are both 3, and at this point, K1 and K2 are both 5. And at this point, K1 and K2 are both 7, right? So what they're both equal to could be, we should think of as a function, right, of on the surface, which I can think of as a function of u and v. And so when we compute this, then we can do the product rule here. Now, the first term we can do is minus k x uv. That's taking the derivative of this term. And then we can take the derivative of this term, which is going to be, I don't like my board work here. It's kind of cramped. Let me just, okay, still want to get it in here though. Negative k x uv. And then the second term is negative k sub u, right? When we take the derivative in the xu direction, that's also a partial derivative with respect to u times xv. And then we do the same thing down here too. We got negative k x. Now this would be vu, uv, but it's the same thing, right? The order doesn't matter. So these first two terms are the same. And then minus k v times xu. Okay. Now these two terms are the same, and everything equals this. Like this equals all that, right? It's kind of a cool calculation. So therefore, this equals that, right? So what we have from all of this is that ku xu is equal to kv xv. But xu and xv are linearly independent. So how is it possible that a multiple of them can be equal? The only possibility is if that multiple is 0, right, in both cases. And so it must be that ku is 0 and kv is 0. But those are partial derivatives. And that's true everywhere. If the partial derivatives are 0 everywhere, then that means that k of u comma v is equal to a constant k. It does not depend on u and v. So it's constant. Okay. Say this is constant. Okay, pretty clever proof actually, right? You can only imagine people are just messing around with things for quite a bit to find that proof. Quite nice, very clever.
How did we guarantee rigorously that xu and xv are linearly independent?
Oh, that's an assumption. Yeah, so early on we're defining what a surface is we say, suppose you have a parameterization x of u comma v such that xu and xv are linearly independent at every point. Yeah, and we have to assume that, otherwise our surface might not be two-dimensional, right? So it's not all possible images. It could all map to a point or something crazy like that, or all map to a line. Right? We want to be full two-dimensional. We need xu and xv to be linearly independent at every point. Good question. Other questions? Yes?
If we have in that middle step that negative ku xv equals negative kv xu, how do we bring that down to ku xu?
Oh, okay. So we have that this equals that, right?
Sure.
And so these two, the underlying terms here cancel, right? Because it's the same in both cases.
Mm-hmm.
And so therefore this equals that.
But aren't we writing a different equality down there? Ku xu? Not.
Oh, I'm sorry. You caught a mistake. I owe you $20 or something. Okay. Ku xv equals kv xu. Thank you. And then, yeah, so I was, shame on the rest of you. But I mean, you probably saw it and didn't say anything, right? You gotta say something. Okay, you know what I meant. Thank you, Evan. Okay, so so anyway, so we get the same conclusion. Ku and kv are both 0, and so therefore k of u comma v is a constant. And it's a constant, by the way, technically on each coordinate chart. but the coordinate charts cover the whole surface, right? So therefore it's constant on the whole surface. Okay. And then that gives us two cases. Case 1, k equals 0. Now if k equals 0, we already know that that means that the shape operator for any vector v, that therefore has to equal 0. Why? Because if k1 and k2 are both 0, that means that a here is just 0, right? And so the shape operator is 0. We already have a theorem in the book that implies that we get a plane. And roughly speaking, I don't think I proved that in class. I think I skipped it, right? But if the shape operator is 0, then the intuition, right, means that, what was the definition of the shape operator, right? It means that the covariant derivative of u in every direction is 0, so that means that u here is a constant. So you have a constant normal vector everywhere, and so you figure, okay, it must be a plane. Right. And the book shows you how I prove that rigorously. Okay, now case 2, suppose k is not equal to 0. Then this is one of my favorite proofs, and I do put it on the midterm sometimes, so make sure you learn it. Because it's just so elegant. All right, and then by the way, you can use this. This is a technique you can use to prove other things too, and we will. What you do is you say, okay, if k is not equal to 0, oh, it's going to be a sphere, isn't it? Okay, and we suppose you actually believe that, right? And so you're like, okay, this x of u comma v, you're like, okay, that's going to make up a sphere. Well, let me show you how you can reason this magical proof. You say, okay, I figure it's going to be a sphere. I think to be able to prove something, you have to be an optimist. You have to say, well, if there was a proof, what would it look like? Because can you imagine a proof that says it's part of a sphere if you never computed where the center of the sphere was? I can't, right? I mean, to say it's a sphere, you have to say where the center is and what the radius is, and say it's a sphere with the center here and radius whatever, right? Okay. And so, okay, well, where is the center of that sphere? Well, if you had x of u comma v, right? So that's some point here, x of u comma v. And then you've got your u vector. I'll go ahead. Which way do y'all want to have u pointing in or out? Want to have it pointing out? Okay. Well, I'll do out. Okay, and then we'll just figure it out. Okay. So this is capital U. It would also work for n. Now, if capital U is pointing out, do y'all remember then that the shape operator? These are actually k1 and k2 are both negative 1 over r. I think. Is that right? Did I get, or no, or is it positive?
Just turning away.
Shape operator is negative.
The normal.
Okay, so then in this case, then we would have k1 equals k2 equals negative 1 over r? Is it? Okay, I was just going to make sure I get the sign right here. Yeah, I think that's right? So we've done this example. You guys are more expert on it than I am. Okay, great. So if we want to, and so this distance right here, by the way, is r, right? And so if we have the point P here, right, represented by x of u comma v, what we could do is we need to add in a multiple of u, actually a negative multiple of u, right? And what we need to do is, so this point right here is center is going to be P minus 1 over minus r u. Do you guys agree? You start with the point P, and then you need to take negative u multiplied by r, and that'll get you to the center, right? Okay. And so, but minus r, that's just 1 over k, right? So what I can do is say plus 1 over k times u, and that will get me to the center in the case of a sphere. Agreed? Okay, so this expression isn't some random expression. It's the expression that gives me the center of a sphere, if it's a sphere. So I'm kind of thinking optimistically. I'm like, well, if it is a sphere, that would give me the center, right? And then what you do is you say, well, let's look at this expression. And let's compute the partial. This is a function of u and v. And let's compute everything we can about it. Let's take its derivative. I mean, that's not a big, well, I don't know. What do you want to do? You guys ever have friends, you're like, hey, what do you want to do tonight? I don't know. What do you want to do? Like, okay, we have an expression. Well, I don't know. I mean, take this derivative. What else is there to do, right? We know calculus, right? So you should probably take the derivative of everything, right? Just to see what you get, right? And when you do that, of course, by definition, you get xu here. That's the partial derivative of x plus 1 over k. And then what is the partial derivative? Then we get this u sub u here. And then you look at that for a second, and you're like, wait a second. Isn't the u sub u, isn't that just like the negative shape operator of xu? Isn't that, right? It is, right? Yeah. That's what u sub u is. And then wait a second, but isn't x sub u an eigenvalue? And isn't that eigenvalue equal to k? Yeah. And then isn't k divided by k equal to 1? And then we get 1 minus 1, xu minus xu, and this equals 0? Yeah. So the u partial derivative of that bracketed expression is 0. Would you be willing to believe that the v partial derivative of that bracketed expression is also 0? Same calculation. And so that means the bracketed expression is constant. And so it equals some fixed point. Let's call it this fixed point Q, I guess. I don't know. Okay. So we proved something. And then you stare at this a bit, and you realize, wait a second, if I just subtract, that means x of u comma v is equal to minus q, bring this to the other side, right? This equals negative 1 over k u. I now take the norm of both sides. The norm of this is equal to the norm of that. But wait, so but the length of u is 1, so I get equals a constant 1 over k. But wait a second, isn't that the definition of a sphere? It says that this x of u comma v is always a constant distance from this magical point q we computed, which is the definition of a sphere, isn't it? Yes.
Can you explain?
And what's the radius? The radius is 1 over k. So we'll just define that to be the radius. Got a question?
Yeah. Can you explain why
absolutely. I have k, I should say.
we're taking the norm of that equality?
Cleverness. We derive this, okay? So the fact that the partial derivatives are constant, these two things, right, imply this, right?
Sure.
And then stare at it for long enough, you realize it's basically the equation of a sphere. It's saying that this thing always has length, a constant length, namely 1 over absolute value k. Because this has length 1, this is a vector, right? So it's saying that the distance between a point on the surface, xuv, and this fixed point q is always the same. So it's saying, so if I just move this to this side and that to that side and take normal of both sides, you can so just play around with it. You stare at it for long enough until you play around with it and realize, oh, this proves it's a sphere. It's kind of a trial and error thing. I mean, keep in mind that you've got years to figure this out, right? So there's no time limit, right? Stare at it long enough, yep.
Did we not assume it was a sphere by our first line?
No. Okay, great question. No, we were inspired by we were hopelessly optimistic that it might be a sphere. And then we proved it was a sphere. So what we did is this expression in brackets was inspired by, the reason we wrote that expression down was because it's like, it's probably a sphere. Okay, what would the center be, right? So that's, the fact that we were guessing the answer was a sphere is why we were clever enough to write this expression down. But now let me tell you how the proof goes, how it's presented, if you want to show someone how smart you are. Okay? And this is, the book does it to some extent. I think the book does it this way. So now let me present it the way the book presented. Case 1, if k is 0, shape operator is 0, you get a plane, easy. Case 2, k is not equal to 0. Because I'm so clever, right? And don't ask me how I ever came up with this. Consider this expression here. And then you're like, well, where'd you get that from? Well, I guess I'm just smart, right? Okay. And then notice that this magical expression, when you take d du of it, oh, look at this, magic, you get 0, right? And then you're like, how did you know it was going to be 0? It's like, well, sometimes I just knew.
I start doing this on my homework.
And then look, the v partial derivative is 0. He's like, how did you know it was going to be 0? That's like magical. And he's like, well, I guess I'm just smarter than you. Okay, I mean, I'm just very clever. Well, look, I'm a professional. I'm a professional, right? And they're like, wow, that's really clever. I mean, how did you know, right? Well, and then you prove this identity, and then you say, oh, look, it's a sphere, and then look, it's a proof, right? We didn't assume it was a sphere. We proved it was a sphere. Okay? But the reason I presented it the first way the first time is I'm trying to reveal the tricks, the sleight of hand. Like, okay, where did that idea come from, right? Because whenever you see a proof like this, I think it is important to try to look behind the curtain, right, and say, wait a second, what's the trick? Like, how did you do that, right? And the answer is, like, we know the answer is a sphere, right? And so, hey, what's this? How are you going to prove it's a sphere if you never compute what the center of the sphere is, right? How could you I mean, the equation for a sphere involves, it says your constant distance from the center, one way or the other. Well, where's the center? Okay, well, there's the center. It's p minus whatever the radius of the sphere is times u, right? By the way, had u been pointing in, then it'd be plus ru, and k1, k2 would be the opposite sign. We actually get the same formula here. Okay? And so we realize that, okay, look, r is just negative 1 over k. And so if we look at, so if I want to get p minus ru, then there's my p, that's the point of the sphere, and then minus r is just negative, it's just 1 over k, then times u. And so, okay, that should be giving me, okay, I think that's the expression that should give me the center of the sphere. For any point, doesn't matter which point you take on the sphere, this expression should give me the center of the sphere, which isn't moving. Like, independent of u and v, I'm going to get the center of the sphere. It's a fixed point, right? And so I already know that if I did this correctly, for a sphere, if I compute this and this, I better get 0, right? And so I know this equals 0 when it's a sphere. And so I'm not actually that surprised when I find out that it equals 0 in general, just assuming that k1, k2 are constant, which I figure means it's probably a sphere. And then, okay, but then what does that mean? It means I have the equation for the center here, but then you just move things around algebraically. You're like, okay, the distance from fixed point is equal to r, okay, sphere radius r, where r is 1 over absolute value k. It's a beautiful proof. Can we agree? Quite beautiful. Also pretty short. I mean, not a medium. I'm going to call it a medium length because we got step 1, prove that k is constant, right? That was clever too. Step 2, figure out that it's either a plane or a sphere. So, really take it in, enjoy this proof. It's really quite nice, I think. Any questions before we move on? Yes.
Are we using some sort of like continuity assumptions? Because it seems like if you have like a cone, then it sort of satisfies the condition. But I guess the issue is like the point of the bottom.
Okay, so 2 things. We're always going to assume that our surfaces are smooth everywhere. But you could take a cone and delete the cone point, right? And that is actually smooth. But K1 doesn't equal K2 for a cone. So on a cone, the Gauss curvature is 0. That's true. But 1 K1, let's just look at that real quick. A cone. Let's see here. We'll pick this point here, right? The tangent plane is got one along the circle, right, and then one along the spine of the cone, or what do you want to call it, right? And you can see that it's curving around the circle direction, right? So but then this direction is flat.
Okay. Well, maybe something like a rectangular prism or something.
Rectangular prism. Rectangular prism. Oh, okay. I got you. Okay. Remember my vocabulary stuff. It's always what I struggle with. Okay, there you go, like this, right?
Yeah.
So okay, yeah. I mean, but this is piecewise planes, right? So if I delete the plates, the parts, like delete the singular parts where it's not smooth, right? Then I really have like six parts of planes, right? And so it falls into our theorem. And otherwise, like the way I like to think, like I said, the way I think of things that have corners and stuff is to think of limits of smooth things, right? And so if we were to round this out a little bit on the scale of epsilon, right, as epsilon goes to 0, then it's not going to be umbilic on the corners here. You know, for the rounded out things, and so therefore I would because it's a limit of things, you know, that are not umbilic, then I would tend to think of that as not umbilic at the corner. I would think of it as one of the principal curvatures is 0 along the straight line, right, and the other one is sort of like infinitely big, plus or minus infinity, or it's curving super fast. Because that's what I get when I smooth it out and to take a limit. Yes?
So another factor of having an umbilical point is
Mhm.
that that's the only time when A, your matrix for the shape operator is a multiple of the identity.
Yep.
Does that have any relation to the fact that the Gauss map is mapping out a sphere and this shape is also a sphere?
Okay, so the Gauss map is the image, the target is a sphere, right?
Yeah.
Let me think. There's probably some connection somewhere. Are there questions? Yes.
If you have like a patch of spheres, that also work, or is it the same explanation as?
Oh yeah, patch of a sphere. So this theorem, I think a surface consisting entirely of umbilic points is, I think technically it should be a part of a plane or a part of a sphere. And that's what we've proved, that each connected component of it is part of a plane or part of a sphere. Yeah, thank you. It probably says that in the book correctly, and I gave an abridged version here. Yeah. So, and of course, if it doesn't have a boundary, then it just goes all, it's an infinite plane, and it's a completely closed up sphere, right? But it could be half a sphere, for example, that would also be correct. Yes, thank you. Other questions? Okay, so this goes us to the next conjecture, or question, right? Which is, suppose we have a surface, okay, a sphere here, right? A sphere has, by the way, the Gauss curvature of a sphere is the product of these, these principal curvatures, which is 1 over r squared, right? So a sphere has Gauss curvature 1 over r squared, which is constant, right? That's constant Gauss curvature. Can someone give me another surface which has constant Gauss curvature?
Plane.
A plane, yes. Now a plane goes infinitely far off, right? It's infinitely big. And so let's suppose that our surface is has no boundary and it's bounded, okay? So I don't want it to go off infinitely, right? So let's suppose that it's no boundary, so no edges, right? And it also doesn't go off infinitely far in some direction, right? So in other words, I want it to be in some finite space, right? Can you think of another surface that has constant Gauss curvature? Well, a cylinder technically goes off forever, right? Or it has a boundary, right? One or the other. So if I say, so by examples and counterexamples, our first thing is, okay, if K has constant Gauss curvature, as we create this, actually, can y'all imagine taking a tennis ball and cutting it in half? And now I have half a tennis ball, but I assume it's hollow on the inside, right? Okay, take all that out. So just think of a rigid surface. Actually, maybe tennis ball's not quite, because I don't want the surface to stretch. Okay, I want it to be made out of, let's say, paper, right? And or hard plastic that won't stretch, or reasonably hard. But I can squeeze that northern hemisphere. Do y'all see that? And it will be kind of an oval around the equator. And it turns out I can do that without actually stretching any of the distances. I actually am preserving the intrinsic geometry of the half a tennis ball when I do that. Now what's interesting is if I have a whole sphere, I can't. A whole sphere is perfectly rigid. If you don't allow stretching of the ball, it's perfectly rigid. But half a sphere is not. Okay, now how do you know that? Well, I actually encourage you to get half a sphere and play with it sometime if you ever can, right? It's just a fact. Okay? And so if you say, hey, what are some constant Gauss curvature surfaces? Well, actually, you can just take, you take a plane, right? You could, by the way, this has constant Gauss curvature too, doesn't it? And then this has constant Gauss curvature, doesn't it? Because k equals 0 everywhere. It's part of a plane. Intrinsic geometry is flat, right? And so there's actually a lot of things that have constant Gauss curvature. But they're all kind of parts of planes, right? And planes are, this thing would go off infinitely, right? So if I say, okay, wait a second. So conjecture, all bounded, no boundary surfaces with constant Gauss curvature K are. So now why did we come up with these hypotheses? Well, we're ruling things out, right? If it's not, I want to get rid of all the planes. Like a plane is unbounded, right? But also a cylinder, right, has 0 Gauss curvature, right? And that's unbounded, right? And so I can get rid of a whole category of counterexamples to my conjecture, right? If I get rid of all the things that are unbounded. And I have to make sure there's no boundary, because otherwise then I can just take a cylinder and have a boundary, and now that's bounded, right? Okay. So, but if I say, okay, all bounded, no boundary, what I'm trying to do is I want the answer to be just a sphere. You guys, so I'm coming up with a hypothesis to rule out everything else. Okay.
What about a donut?
And it turns out we can't think of any other examples, and so the correct conjecture is to conject a sphere. Now, if you look at a donut, later on we'll prove that the integral of the Gauss curvature of a donut is equal to 0. And it turns out it's positive in some places and negative in other places. But you might thinking, why don't you just make k equals 0 everywhere? And that's actually a good idea. And guess what? You can get a k equals 0 everywhere donut in 4 dimensions, but not 3 dimensions. Okay. So let's prove that first. Okay, because that's actually already the first step of a proof we're about to do. Okay. But yeah, if you actually compute this, and you guys have done problems where you're computing the Gauss curvature of a, I think you actually had a problem. Was that last week or this week where you compute the Gauss curvature of a donut?
Last week.
Last week?
Yeah.
Okay. And what you found is it's both positive and negative in some places, so it's not constant, right? So okay, so that's out. So anyway, what you find out is this is a pretty good conjecture here, right? Like if you think about it, and then you talk to your friends, and they think about it. Anyone think of a counterexample? And this conjecture is something that comes up over the period of weeks and months of people discussing example, counterexample, right? Well, someone makes a conjecture. Most conjectures are disproved because they're like, oh, counterexample. Oh, okay, yeah, you're right. Stupid conjecture, right? And then we don't like to talk about the conjectures that were false, right? We just pretend like it never happened, right? And so then certain conjectures survive, and then they get proved. Okay, and this one has a proof. So it's a theorem. It's actually really hard to prove. Okay, this is not easy to prove. Okay, I'm not even going to show you the whole proof. The book has the detail. Let me tell you the hard part. There's this guy named Hilbert, all right, and greatest mathematician of his generation, around right before or during the time of World War I. Which, by the way, isn't that weird? How Hilbert is this great mathematician. He's German. His colleagues are French and English and American. And next thing you know, we're at war. World War I, millions of people die, right? Horrible. And I don't know. It's like the mathematicians see the ridiculousness of it at the time. Let me just say for the record, right? They don't like it. On the other hand, I mean, what are you going to do, right? I mean, everybody supports their home team, I suppose, right? But they also are against war in general, typically. If someone could explain to me what World War I was all about and why it was a good idea, please do. I'd like to know. All right, but I think what's interesting about World War I, if we just take a little tangent here, to Miss Hilbert, his era, right, is that we can't remember what it was about anymore. In other words, we were sufficiently removed from the propaganda of the day that now it just looks stupid. And I think that's interesting, right? I'm not saying they didn't. Of course, they had reasons. Of course, they did. I'm sure they had all kinds of very compelling reasons. I mean, they probably had all. I mean, at the time, it probably was pretty clear what the war was about, right? I'd just be kind of curious. I mean, I'm sure you can dig up. I know. Didn't they say that? I think among other things, they said that the Germans ate babies. I think that actually was said. And things get very personal because I mean, millions of people are dying. And if you go to MIT, where I taught 20 years ago, there was they engraved the great names of the great mathematicians on the building. And they've got Newton and Lagrange and Laplace and all these great English and French mathematicians. Not a single German mathematician, no Gauss, no Riemann, because the building was built around World War I apparently, and we are not putting a German name up there, right? I think mathematicians are interesting because we have an international community. And so we are also people, of course, but it just seems, ridiculously tragic to think of Hilbert here, who's one of the great mathematicians, on their other side, right? And we're killing his family, and his family are killing our families, and things like this. It's just horribly tragic. Okay, so then we have this limit of 3.5.6 that Hilbert proved. And I guess that we can give credit to Hilbert now that World War I is over and we don't hold a grudge anymore, I guess. Somehow or another we're over it. Sufficient time has passed. One of the great mathematicians of all time. So what he showed was that suppose that you have a surface, and suppose there's some point P, and let's suppose that, by the way, I'm going to follow the book. Okay, remember I said that K1 should be less than or equal to K2, but apparently in this case we're going to have K1 greater than or equal to K2. Okay, just warn you. And so let's suppose K1 is, wait a second. Yeah, that's what they do, okay. K1 is maximized at this point, and then K2 is minimized at this point. Okay? So in other words, the larger of the two numbers we'll call K1, the smaller of the two numbers we'll call K2, but I guess all it has to do is be a local max. We're going to have K1 greater than K2. So, but anyway, if you go left or right in any direction, you vary around the point P, K1 is locally maximized here, and then K2 is locally minimized. So imagine you have K1 is not equal to K2, and K1 is defined to be bigger than K2. In that neighborhood, K1 is a local max and K2 is a local min. So that those hypotheses imply, so K1 maximized and K2 minimized at a point P implies that at that point the Gauss curvature must be less than or equal to 0. Now, how did he prove this lemma? It's actually pretty it's a little bit technical. It's got some steps to it. I'm not going to go into it. It's in the book. I encourage you to look at it. It's a couple of pages. He proves some intricate identities that we're not going to use anywhere else. So I'm just going to leave it, let you look at in the book. So now it turns out this limit can be used to prove the theorem, because what you do is, we know that k is equal to k1 times k2. And so what you do is you say, let p be the maximized k1. Okay, in other words, just choose the point where p maximizes k1. Okay. Now, there's two possibilities. Okay. Possibility one is that at that point p, at p, k1 is greater than k2. The second possibility is at p, k1 is equal to k2. Okay, those are the two possibilities, right? Because either k1, k, we're always defining k1 to be the bigger of the two, to follow the convention of the book. Either they're equal or they're not equal at the point where k1 is maximized. The larger of the two is maximized. But wait a second, but the product is fixed. Okay, remember we're assuming constant Gauss curvature, right? So the point is, if we have a maximum for K1, so we're maximizing K1, we also have a minimum for K2, right? Because the product equals a fixed thing, right? By the way, I need to go back and fill in a step. And I said I would do it earlier, and I should have done it at that time. But let's see, let's draw a picture here. If you take any surface, remember we said that it has to be finite, it has to be contained in a bounded region? What that means is there's some, you can put it inside of a sphere. Okay, for some sphere, it's inside a sphere entirely. Now let's go ahead and say, let's talk about spheres centered at the origin. Then what I can do is I can say, well, don't just put it inside some sphere, put it in the smallest sphere. Like just shrink that sphere down to where it just barely touches. So maybe the origin is right here, right? And then the smallest sphere that contains it is like this sphere here, okay? You guys see what I'm doing? Whoops. The center is here, okay? You guys get the idea? And so there's going to be some first point of contact here, right? And here's what's interesting. If you do this, let's go ahead and choose U to be pointing in. You guys, when you choose U to be pointing in, that way K1 and K2 are both plus 1 over R instead of minus 1 over R. Okay. Then the point is, at this point, it must be that K1 and K2 are both bigger than or equal to 1 over R, where R is the radius of this sphere here. Why? Because it curves even more, right, than the sphere, right? If, remember what K1, K2 are? They're the max and mins of normal curvature, which also should be called cross-sectional curvature, right? But if you look at all the cross-sections, these cross-sections are curves that curve more than circles, right? Because the cross-sections of the sphere, right? I mean, this point here points straight to the center of the sphere, right? And so when I look at the plane containing this U and any circle of little u's, right, the cross-sections are spheres of radius R. And so these cross-sectional curves curve more than the circle of radius R. Therefore, their cross-sectional curvature is more than 1 over R. So therefore, K1 and K2, which are the max and mins, well, all the normal curvatures are bigger than 1 over R. So therefore, the max and mins are bigger than 1 over R. And so therefore, the Gauss curvature is positive at this point. That's, you do all that work just to say, therefore, at that point right there, the Gauss curvature is greater than or equal to 1 over R squared. Okay? Where R is the radius of that circle. Okay, so you can see it's curving more, so that kind of fits with our intuition. But in particular, it's positive. The Gauss curvature is in fact strictly positive and bigger than 1 over R squared. Okay, so that's actually step 1 of the proof. I was put in right here is that, you know, K is equals a constant, but it's a positive constant. Because at one point it's positive, but then you're saying K is a constant, so K is a positive constant. Make sense? So we're trying to figure out all surfaces of constant Gauss curvature. At one point the Gauss curvature is positive, so therefore at every point the Gauss curvature is that same positive constant. Okay? Okay, so since K is positive, then when I say K2 here, K2 is equal to this positive constant divided by K1, right? And so if this is being maximized, then that ratio is being minimized. And so now why is it I can say let P maximize K1? Well, that's where I'm using the no boundary condition, by the way. Well, I mean, what do we know? We know that the maximum of something is either an interior point or a boundary point, right? And so since there's no boundary, it must be an interior point. That's actually how we're using the boundary condition. Which means that, that we have a point where it's a local max for K1 and a local min for K2. So in other words, it really is a local max and local min, which is what you need for limit 3.5.6. It's not, there's no boundary point or anything like this, right? And so that means that the Gauss curvature at that point is less than or equal to 0, but that's a contradiction because we already know the Gauss curvature is of some positive constant. So this first case cannot happen. So we get this all proves, so then this implies that K is less than or equal to 0, which is a contradiction. So what that means then is we got a contradiction. It means we have two possibilities here. This first possibility never happens. It never happens that when you maximize P, when you let P be the point where you maximize K1, it never happens that K1 is actually strictly greater than K2. At that maximum point, K1 equals K2. But their product is equal to that constant, right? And K1 and K2 are defined to be, or more precisely, K1 is defined to be, remember, it's always defined to be the larger of the two eigenvalues. K2 is the smaller of the two. And if I say maximize it and they're equal here, it must be they're equal everywhere. But if K1 and K2 are equal everywhere, then this previous theorem applies. We have a sphere. So it means it's umbilic everywhere, which means a sphere. There you go. I mean, to be more precise about that last step, I mean, you have K1, and then what is K2? K2 is equal to capital K divided by K1, right? These are our two. So when you're maximizing K1, same thing as minimizing K2. If there was some point where K1 was actually bigger than K2, then the maximum would have K1 bigger than K2. So, but there isn't a point where K1 is bigger than K2 anywhere, because if you did, then case 1 would happen when you maximize K1. So therefore, K1 equals K2 everywhere. Therefore, it's umbilic. Therefore, it's a sphere. Not only that, I can tell you what the radius is, because we know what the Gauss curvature of a sphere is. It's K equals 1 over r squared. So it's a sphere of radius r. But what's r? I take 1 over K and take the square root, right? Sphere radius, square root of 1 over capital K. Pretty cool stuff. Now I did sort of have a magical spot there. The magical spot was this limit 3.5.6 that Hilbert proved, and that's got some intricacy to it. It's a bit of a it's 20 minutes to present it, so let's not spend 20 minutes that way. But I encourage y'all to look at it. And those questions? Yes?
Why in the case 1 do we know that K is less than or equal to 0?
Oh, that's limit 3.5.6. That's the part I didn't prove. Because we have K1's locally maximized, K2's locally minimized at the same point, then capital K is less than or equal to 0. Yes, good question. Okay, so that's some theorems about Gauss curvature. What we're going to do next week is get into mean curvature as well. And so let me introduce that in the last 5 minutes here. Mean curvature is very, very cool. also very important. My research involves both mean curvature and Gauss curvature. So I mean, this is not just undergraduate topics. It's something that you talk about for your whole career as a differential geometer. They're both of huge importance. Remember what mean curvature is? It's the trace curvature. It's K1 plus K2 is what 2H is, right? Or H when you graduate from this class. And so one thing you can ask is, there's something as a definition here, first of all, and that is a surface with H equal to 0. Remember what H is? Remember H is equal to K1 plus K2 over 2, right? Is called a minimal surface. Another bad name. Bad name after bad name after bad name. Okay? Now, why do they call it a minimal surface? Well, it turns out that minimal surfaces locally minimize surface area. Okay? So, can we give me an example of a minimal surface? Surface that has K1 plus K2 over 2 equal to 0.
Catenoid?
Catenoid is a simpler one. What's the simplest example, though? A plane, right? And you guys agree that, now what does it mean to say it locally minimizes surface? So if you look at a plane, if I cut out, put a hole in the surface and then fill in with anything else, the area will be larger, right? And so what a minimal surface, the property it has is that, and so what's another example would be a catenoid, right? So you take a y equal hyperbolic cosine and then rotate it around an axis here, right? Rotate it around. This is y equal hyperbolic cosine of x, and various scalings of it. That's a catenoid. And this also has h equal to 0. Plane has h equal to 0. And this is a catenoid. And they locally minimize area. Meaning what? Meaning that if I cut out a small part of it and then replace it with something else, the area will be larger. Okay? So in that sense, it's reasonably named. If they had called it like a local minimal surface, but it's not. They're not globally minimizing necessarily. The plane is globally minimizing. No matter how big the patch I cut out, it is the minimum area. But actually, a catenoid is not. It turns out it might actually be less area to go across like this. So if you cut out a big enough area, it's just like go straight across. Like, on the large scale, a catenoid looks like this, right? Y equal hyperbolic cosine. Then this gets rotated around. Can you all see what I'm trying to draw here? Okay. And it keeps on going, all right? And so on, right? And the point is, if I cut out this whole thing here, it'd just be less area just to go straight across like here, and to get a cylinder here, okay? So circular cylinder would actually be less area.
It wouldn't even dip in a little bit.
It would dip in a little bit.
Okay.
I mean, the minimal thing, yeah. But actually, it would dip in a little bit, and guess what? The thing that actually does minimize will be a different catenoid. It would still be a catenoid, actually, just a different catenoid. And but the point is, so they're not globally area minimizing, but they're locally area minimizing. And they're also, but even globally, they're critical points of the area functional. They're critical points of the area functional. It means, what is H? What's really important about H is that if I have a surface, one of the simplest things I can do, given a surface M, is I can say, what's the area of the surface? And so I can say, A. I talk about the area of M, right? Okay, now what does that equal? It equals the formula for it. We take the integral over M of 1 times the thing you integrate to get area, right? That's how I would write. Okay, dA is the area form that you integrate, and you compute it in your multivariable calculus class. Well, here's an interesting question, and I actually do this all the time, okay? What if I flow this surface a little bit? I want to change it, okay? Well, what I can do is I can leave it the same everywhere, but in other places I'll just move it a little bit, okay? And so what we can do is we can talk about, well, how fast are you flowing it? Let's talk about the perpendicular speed, okay? And so let's let eta here be the perpendicular speed that we move. So eta is a function on my surface M, right? And by the way, I can talk about the volume, right? Let me give you a formula that probably makes sense to you. If I say, what's the volume of M, I would integrate everything on the inside of M, right? But if I then say, what is the rate of change, d dt, of the volume of M under this flow, okay? It's the shell method that you've used before. It's just the integral over M of the speed of the flow times dA, eta. Integral of eta dA. Does that seem reasonable to you guys? If eta is 0, you're not flowing at all. More generally, eta is the thickness of the shell you're putting on there, right? And so it's surface area times the thickness of the shell, right? And there's your surface area, and there's the thickness of the shell, right? And so this hopefully is intuitive. Does that seem reasonably intuitive? You believe me? Okay. And this is a definition of dA, and this is a consequence. Okay. This is volume. But then the next most basic question is, well, what's the rate of change of the area? This is, by the way, this is a little bit more subtle. How's the area changing, right? Okay, now I can't really do a visualization. And we'll compute the formula for this later, but let me tell you what the answer is, because it gives you intuition for mean curvature and why it's so important, is that it equals the integral over M and I want to make sure I use our convention. Put the sign there, I guess I'll show it. It's just twice the mean curvature. I think there's a minus sign because the convention's times the speed of the flow, dA. So instead of integrating the speed of the flow, I think this might be for the normal pointing out. Okay, so if you have the unit normal pointing out, you have to choose your convention because that changes the sign of the mean curvature, right? Of K1, K2, and therefore H, which is K1 plus K2 over 2. So I think if you have U pointing out, then the mean curvature of a sphere, for example, is negative 1 over r, I think. And so this is the formula for the rate of change. In other words, it's sort of like the rate of change of the volume, integral of eta dA. That part here didn't change, right? But then the mean curvature term is what you multiply by to get the rate of change of area. So in some sense, mean curvature is roughly the ratio of the rate of change of area to the rate of change of volume. Or up to, except for the factor of -2 there, okay? And so, in other words, if h is 0, now you see why it's a critical point. Like if you have a 0, like a plane has h equals 0, just so the first order, when you do a perturbation, you know, if you're a local min, for example, right, we know that the slope is 0 at a local min, right? And so if you think of this plane and you're perturbed, you're going to flow it up or down, right? Well, the area is bigger in all cases, right? But when the flow is at t equal to 0, that's where you have the plane, right? And that's locally minimizing area. And so we know that this is going to be 0, but the formula that tells you it's 0 is that the mean curvature is 0. In fact, any surface that has 0 mean curvature will be a critical point of area. Right? And usually a local min, if your variation is on a small enough region, it will always be a local min. But all it actually tells you is that it's a critical point. And it says the slope is 0, so it could be a local max. Or it could be more likely, you know, it's a very high dimensional space of possible flows. You can do infinite dimensional space, really. And so it's probably more like a local min in some directions and a local max in other directions. What do we call that? Is that a saddle point?
Sure.
Somebody all call it? Okay. So it's a critical point, more generally. Okay, any questions? And so anyway, you can you can compute. What does the book do? You can compute what are all surfaces with 0 mean curvature. You can compute a formula for what the mean curvature is in terms of a graph. It turns out a catenoid are all possible surfaces of rotation that have 0 mean curvature. And that just turns into a second order ODE problem to solve. And we can discuss that a little bit next time. Okay, see you guys next time.